Welcome back, listeners, to another exciting episode of Operating Systems Crashcast. I'm your host, Victor, and today we're diving into a critical topic in process management, Deadlock Characterization. Joining me as always is my co-host, Sheila. Are you ready to untangle the web of deadlocks, Sheila?
Absolutely, Victor. Deadlocks are a fascinating and crucial concept in operating systems. Let's start by defining what a deadlock is for our listeners.
Great idea, Sheila. A deadlock is a situation in a computer system where two or more processes are unable to proceed because each is waiting for the other to release a resource. It's like a traffic jam where cars are blocking each other's paths and no one can move forward.
That's a perfect analogy, Victor. Now, let's dive into the 4 necessary conditions for a deadlock to occur. These are known as the Kaufman conditions, named after computer scientist Edward G. Kaufman, Jr. Can you walk us through them?
Certainly. The first condition is mutual exclusion. This means that at least one resource must be held in a non-shareable mode, so only one process can use the resource at a time. For example, a printer can only be used by one process at a time.
The second condition is hold and wait. This occurs when a process is holding at least one resource while simultaneously requesting additional resources that are currently being held by other processes. It's like a driver holding onto their parking spot while waiting for another spot to open up.
Exactly. The third condition is no preemption. This means that resources cannot be forcibly taken away from a process. They must be released voluntarily by the process holding them. In our traffic analogy, it's like not being able to tow away a car that's blocking the road.
And the final condition is circular wait. This happens when there's a set of waiting processes, each waiting for a resource held by another process in the set. It creates a circular chain of dependencies. Imagine a roundabout where each car is waiting for the car in front of it to move. But no one can move because they're all blocking each other.
Great explanation, Sheila. It's important to note that all 4 of these conditions must be present simultaneously for a deadlock to occur. If even one of these conditions is not met, a deadlock cannot happen.
That's a crucial point, Victor. Now let's talk about a tool that helps us visualize and analyze deadlocks, the resource allocation graph. Can you explain what this is?
Certainly. A resource allocation graph is a directed graph that represents the state of a system in terms of processes, resources, and their relationships. In this graph, processes are represented by circles and resources are represented by squares. Arrows show the relationships between them.
So, how do we interpret these arrows, Victor?
Great question. An arrow from a process to a resource means the process is requesting that resource. An arrow from a resource to a process means the resource has been allocated to that process. If we see a cycle in this graph, it indicates a potential deadlock.
That's fascinating. Can you give an example of how this might look in a real system?
Sure. Imagine we have 2 processes, P1 and P2, and 2 resources, R1 and R2. P1 is holding R1 and requesting R2, while P2 is holding R2 and requesting R1. In our graph, we'd see arrows from R1 to P1, P1 to R2, R2 to P2, and P2 to R1 forming a cycle. This cycle indicates a deadlock.
That's a great example, Victor. It really helps visualize how deadlocks can occur. Now, before we wrap up, let's quickly discuss the difference between deadlock and starvation. They're related concepts, but not quite the same, right?
Absolutely, Sheila. While both deadlock and starvation involve processes unable to make progress, they're distinct scenarios. In a deadlock, processes are stuck waiting for each other indefinitely. Starvation, on the other hand, occurs when a process is indefinitely denied necessary resources to complete its task, often due to poor resource allocation strategies.
So, in starvation, the process could potentially continue if it got the resources, whereas in a deadlock, the processes are fundamentally stuck.
Exactly. That's a great way to distinguish them. Now, let's recap what we've covered today. We defined deadlocks as situations where processes are unable to proceed due to resource conflicts. We discussed the 4 necessary conditions for deadlocks: mutual exclusion, hold and wait, no preemption, and circular wait. We also explored resource allocation graphs as a tool for visualizing potential deadlocks. And finally, we distinguished between deadlocks and starvation.
This has been an incredibly informative discussion, Victor. Deadlocks are a critical concept in operating systems, and understanding how to characterize them is crucial for both system design and troubleshooting.
Absolutely, Sheila. And that wraps up our episode on deadlock characterization. Thanks to all our listeners for tuning in. Remember, in the world of operating systems, it's always better to prevent a deadlock than to be caught in one. Until next time, keep your processes running smoothly.